Hello everyone, welcome to lecture 8 of this course. In the previous lecture we discussed charge numerals, successor function, the functions for add, multiply and exponentiation and the is 0 function. Today we are going to discuss the design of some Boolean operations and some combinators. So first we take up the design of the OR function. Our starting point for the design would be we start from if function. So recall that if was designed in this way, there are 3 parameters b, x, y, and we said if b is true, b then x and y, like that. We interpreted the b is true, we are going to get the first argument, then like this. Now or we know that there are 2 arguments x and y, and if any one of them is true, the result will be true and the result will be false when both of them are false. So this we know. So then our OR function design, then the design we may start with, instead of 3 now we have lambda x dot lambda y, and our first attempt will be, this will be our attempt 1. So we may say like this, from this bxy we may say okay, let it be xy. This would be our first attempt. Anyone who is proceeding with it, who might think that okay, if is like this, then why not OR will be like this. Fine. Now if we supply the argument, so if we do OR of say false, say OR of false or false. So that means lambda x, lambda y, x y, false, false. This beta reduces to false, false. Now answer should be false and not false, false. Likewise, if you do any other combination like true, true, it will be true, true or true, false, something like that. But it will not become one, it will not evaluate to false, neither will evaluate. So that means our first attempt is not correct. So we proceed then. So we move on to the design then. So our attempt 2 would be, then we feel that OR will be then defined lambda x, lambda y. So now we also know that true, if there are 2 arguments c1 and c2, that will give us c1, and false of c1 c2, this will give us c2. This we know, that is a constant for Boolean constant, there is defined, they will evaluate to this. So then that lambda x, lambda y, so now we say if let the first parameter be x, then as from this we can see that if it is true, then there will be 2 more arguments. Similarly for false, there will be 2 more arguments. So thus we say there will be these 2 terms, there will be 2 sub terms here in this one. So this is 1 and this is 2. So the structure will be lambda x, lambda y, then x followed by term 1 and term 2. So this is term 1, this is term 2. Now let us do the Boolean. So if x is equal to true, so it will be true. This is, we are writing t1, this will be t2. So if it is true, if one of the variable value is true, the answer will be true. So that means then c1 that we had in true, it is the first argument, then the first argument we can write true. We are not now bothered about the second argument. So t1 must be true, that we have understood. So then then we can rewrite it, our OR, as we have got, if it is false we will discuss later, but now it will be lambda x dot lambda y, x true, this will be then t2. Likewise if we do x is equal to false, so this will be false, first parameter is of no use to us, it will be the second parameter. That means second parameter, now x is false, so that means it will be, if y is false, the answer will be false, if y is true, the answer will be true. So then now we know false also is governed by the, false will return the second argument. So that means answer will be t2. Now t2 is whether it is false or true, we do not know, it will be determined by the value of y. If y is false, answer will be false, if y is true, it will. So this t2 will be then 2, will be y. So if we put these 2 things together, what we have got is our OR as lambda x dot lambda y, then this is x, this is true, this is y. So evaluate, if we do true, so it will be true, true, y, answer is true. If it is false, y is false, so it will be false, true, false, so it will be false, and if it is false, true, true, so answer is true. So we are done. So this we are going to call as version 1. But now let us take a look at it very carefully, and whether we are having a non-lambda, you can say 2 is a constant. So whether we can write a rather simpler term than this one. So if you take a closer look here, we see when x is true, we are writing T1 is true, but then T1 is nothing but this true is nothing but the value of x. It is nothing but the value of x. So then this true is nothing but the value of x. So this is what we then obtain, and this we call version. Version 2 does not have any constant, and then this is our OR function. This is the simple way of saying. So what is it saying? Lambda x dot x dot y. That means if x is true, we are going to get the answer as true, which is x. If x is false, you are going to get the value which is y. So that's it. So OR design we are done. Similarly, we can now design the AND function. So now that we have got the idea of OR, so our AND structure will be also x followed by something and something. So you know that if x is false, the result any one of them is false, the answer is false. It will be true provided both of them are true. So again, as before, we have this term. So we have AND lambda x dot lambda y. We start with x and we have this is term 1, this is term 2. If x is false, the answer will be false. Now false takes second argument. So that means T2 will be equal to false. If x is false, T2 must be false. Now if x is true, then we cannot say the answer is true. Then that is determined by the value of y. That will be determined by the value of y. So if x is true, so this will be true T1, T2. So then answer will be T1. Now T1 will be whatever y value we have. So this will be y. So thus our body will be x, y false. Lambda x, lambda y, x, y false. Now this we are calling as version 1. Now if we again take a closer look, when x is false, we are saying the answer is false. This false is actually the value of x. So then we can say x, y, x. So this is our AND function. So it is worth rewriting these two things together. So we say lambda x dot lambda y, x, y false, and we have lambda x, lambda y, x true y, and we have lambda x, lambda y, x, y, x, and we have lambda x, lambda y, x, x, y. So this is our OR, this is our AND. So in this AND function, we have both this AND and OR, they are the version 2, they do not have any constant terms. They are very simple terms, one is x, x, y, another is x, y, x. So here if it is true, then you are getting first term, if it is false, you are going to second term, and the second term will be the value of y. So if it is true, it will be true and null. And if x is false, we are going to get here false. So this is the design of AND and OR. They are quite similar. The next function that we are going to consider is the NOT function. So that means it will give the, if x is false, we are going to get true, and if x is true, we are going to get the value false. So now there will be only lambda x dot x, and now there is only one argument, and as before we are going to have two terms. So if x is equal to true, so this is T1, this is T2. So T1 will be equal to false. So that means what you are having? You are having true, then this T1 is true. If x is true, T1, it will be T1. X is true, then T1 is false. Because x is true, we are going to return the first one. So that means we have to return false. And if x is false, so this is false, we have to return this part. This part will be true. This part we are going to return true. So if we combine, so it will be lambda x dot x. X is true, then it will be false. X is false, it will be true. So it will be lambda x false true. So not will be lambda x dot x false true. Now we have to see the exclusive OR. So exclusive OR is the same as OR, except when both x and y they equal to true, then the result will be false. So our starting point then would be OR. We have defined lambda x dot lambda y, and we said x, x, y. So now we say if x is equal to true, y is equal to false, then the result will be, result is true. And if x is equal to true, y is equal to true, so it is true and false, so result will be true. So both are true, then the result is false. So here what is happening, this y is as if changed to false value changed to true, and the true value changed to false. So that means it is the negation of this whatever y value that we have. So then we can say exclusive OR lambda x dot lambda y dot x, then the result will be true, means the first component we are going to take, and the first component is the negation of y. So, this is not of y, and we had x y. So, this will be y. So, if x is false, we are going to get the T2, it will be T2. So, T2 is y will give the answer. X is false, it will be y. If x is true, we are going to get not of y. That means, if y is true, then the answer is false. If y is false, answer is true. So, XOR we have completed. So, then we have to see. So, now we have implications. Implication is the next one we have to do. So, that means we know that if P implies Q, this is represented as negation P or Q. That means OR of negation P Q, that is OR of not P Q. So, that is this things we have encoded here. So, it is OR, it is a combination of OR and not. So, implication is A, we have to do A implies B or P implies Q. So, we have x and y parameters. We said x implies B means you do the negation of the first one or y and you have OR of this. So, we are going to get implies. Now, we do if and only if, that means this one, that means this is P implies Q and Q implies P. So, that means we now combine both of them. So, we know how to write implies and we combine with AND. So, it is AND of P implies Q and Y implies P. So, this will be one way of writing implies, that is straightforward like this. But we also know the if and only meaning is that if and only if P implies Q, if and only if Q will be true, when either both P and Q they are both true or they are both false. Either both of them are true or both of them are false. So, this then if we do like this, then we can use AND only, we need not go to implies. That means, we need not have this implies things now. So, we say both x and y are true. So, that means AND xy will give the true, or both of them are false, that means not x not y. So, you take AND of this. So, if both are false, that means not of x will be true, not of y will be true, AND will be true. If both are true, then AND will be true. One of them is true, one of them is false, then this will be false. X is said true, then this will be false, so it will be false. So, we are going to get false. So, this is another way of writing both ways if, that means if and only if is written in this way. So, this completes our discussion on the Boolean operations. So, let us now list the definitions of Boolean functions. So, OR, these are the functions that we have seen. So, OR is lambda x, lambda y, x x y, and will be lambda x, lambda y, x y x. Not is lambda x dot x false true. Again, you can convert to a pure lambda term, replacing false and true with, and exclusive OR is lambda x, lambda x not of y and y. Now, x implies y will be OR of not of x y, and if and only if we are going to write OR, then AND x y, AND of not x not y. So, now we take on some standard combinators. So, these are called S, K and I, and the idea is to obtain complex terms using only these as the basic combinators. So, some arbitrary lambda terms we are going to write in terms of x, S, this is S is actually called substitution, I is the identity function, and K is the, you can say this is the first of these things. The two arguments you are going to get the first term. So, it is called K, historically written K. So, this is the first term and this last one is xz, yz. So, we want to write the Boolean constants true, false. So, first we are going to write true. So, true we know lambda x, lambda y dot x, that is first actually, this true is first. So, that is basically our K, this is given K, this is K. Then next is false, lambda x dot lambda y, this is y. Now, this is not K, this is something different. So, we want to write it in terms of K, I and S. So, our terms can contain S, K, I and S and nothing else. So, how to get the term for false? Now, this is at the beginning you may find some difficulty, but when we gain some experience, so then we can do it quite easily. So, let us say that it will be, if I if we start with k, so we represent k is this one. Now let us do k of I. So k of I beta reduces to lambda y dot I, So that is equal to lambda y dot lambda u dot u. So again that is equal to lambda y. This bracket has actually no purpose, is served by this bracket. So we write it. So we can rename it again, alpha renaming by alpha renaming. So we make this as x, which does not occur here. So this is y and this is y. So this is then our false. So false then can be represented as ki. False will be ki. Now we do the third one, that is SA. Now SA is lambda x dot xx. Now so again what I am doing is I am just verifying. I know the answer, so I am writing it and I am verifying and showing that they are same. But I am not telling you okay how to get SA is this or how to get false from intuition. That part I am not doing. So that part is with maturity, and when we get lot of experience, we will be in a position to design the functions as we have done the exercise for say successor function design and other functions that you have designed. Through that experience, as well as using, when familiar with this, using this x y later on, then you might get a feeling of how to write it straightforward. And also we are going to show some rules, that is a way of transforming. There are rules for transforming an arbitrary lambda term to this SKI that we are going to show, but at this moment we are not in that stage to do that. So I am just showing that okay, I know the result and I am showing you okay, at least we can verify and say that what it is. So here lambda x dot x, we start with s and we do I, si. So I start with s and I will do apply. So s we know as lambda x, lambda y, lambda z. So x z and y z. So si will give us, that means x will be, it will be I z of y z. So beta reduction again this part will give us lambda y or lambda z, I z will be z. So this will be y z. So now we have not achieved our lambda x dot xx. So there are two terms, then we have two terms y and z. So we have to get rid of this y, then only one lambda will be there. So let us then do SII. So SII will give us, then that means this is actually lambda y dot lambda z dot z y z, and there you are applying I. So beta reduction will give us lambda z, z of y is replaced by I. So it will be I z. So you are going to get beta reduction. So beta reduction I am going to get lambda z dot z, I z is again z. So now we have got alpha renaming. So lambda x dot xx. So you have obtained SA. So SA then means SII. SA means SII. And omega is SA. So that is then SII of SII. So thus these simple terms like true, constant terms like true, false, application, self application and omega, all of them can be written in terms of only three combinators. These are S, K and I. So now we take the problem of a little bit more complicated lambda term. So that is again, it is historically called a B combinator. So that is you have x, y, z, x first term is applied to the what is obtained from applying y to z. So it is a kind of composition, y is y of z, and the result is the three functions are composed in some way. That is the whole idea. Now we have a rule that says that, so the way of transforming, as I was discussing, that if I want to transform an arbitrary lambda term to this SKI term, so one rule is that if I have lambda x followed by mn is an application. So we introduce an s, that is a successor. Sorry, it is not successor, it is this S combinator. The S combinator followed by two terms. One is an abstraction of lambda x dot m, another is an abstraction of lambda x dot n. So that is an SKI rule. Another rule says that if I have an abstraction like lambda x dot m where x is not free inside m, then you replace it as km. Using these two rules, we can obtain SKI terms for a given lambda term. So, our technique then, now this term if I look, now this is not in a, this whole term is not in this, neither of the format it is true, but it is just lambda x dot m, there is no other things that are there here. So, the idea here is to see only the inner part. Inner part has only one lambda and our this rule is applicable here. So, and we ignore the x and z. So, we start from the inner part and see whether which rule it matches. Here is this rule it matches, lambda x dot mn. So, then apply SKI rule, we will get s of then lambda x dot x, it will be not like that, x we can give another parameter and we have this form we can get. So, let us say we evaluate this to T1. Now, we move on to, now it will be, now the second part we are going to see, it is lambda y dot, now we are saying lambda y dot T1. Lambda y dot T1 is again lambda y dot T1. T1 has this, D1 is an expression that contains Mn structure, it will have Mn structure. So, then again we repeat this process, we will get again T2. Go on doing it and we evaluate to T3. And if it M is of this structure, if it is lambda x dot M only, then we apply this rule, provided x is not free inside M. However, when we go on doing it T1 to T3, we come up with a very messy, which contains so many x and y and other lambda things. Now, in order to simplify it, we need to know SKI equivalences. So, the idea here is in our, when we study regular expressions, so given a complicated regular expression and we are asked to simplify it, we have the algebraic rules of regular expression and we used to use it repeatedly and then we obtained a quite much simpler regular expression, or rather if we are asked to prove that this regular expression R reduces to R prime. So, we used to do the algebraic rules one after the other in some way and then we obtained R prime. So, the same thing holds there, it is some algebraic rules are the SKI equivalences, some of them we are going to study. That when applied to this, we are going to get the term like this is our desired term, it will get SK. So, then first we are going to study some equivalences and then you can apply method 1 and then you can directly obtain this term from this. So, the other way of solving this problem, instead of, so suppose that given expression, we assume that given expression is correct. If it is indeed so, then our technique is to show behavioral equivalence of these two. One is a given expression B and another is it is equivalent to T, where T is an SKI term. So, we apply the parameters on these two. So, B x y z will give us M, this reduces to M, then T x y z should also reduce to M. If that be the case, we say T is a representation, SKI representation of the given terms B. So, this is a verification, it is not derivation. So, for the present example, let us continue, let us see whether, let us verify this term. So, SKS, we are going to verify whether this is indeed correct SKI representation of this or not. So, let us first do Bxyz. Bxyz, if we do beta reduction, we are going to get x of yz. This we know, this is straightforward, some parameters will go and we are going to get xyz. Now, we want to do SKS k of xyz. So, now we identify this to be P, this to be Q and this to be R, because we know S has 3 parameters. That means S is lambda x, lambda y, lambda z, xz, yz. And if we apply the parameters S of xyz, it becomes xz, yz. So, that means S of PQR will give us PR, QR. Now, PR, QR, what is this PR, QR? PR is KSX and QR is KX. So, this is our first job. So, we are going to do KSX and we are going to do KS. So, KSX, K is our lambda x, lambda y dot x. So, then KS will be equal to lambda y dot s. Then KSX is equal to lambda y dot s of x. Now, a y does not contain here. So, beta reduction will give us s, and kx is lambda y dot x. So, this then transforms to s, and then this is kx is lambda y dot x. So, we have got here s. So, what we have got, this part qr pr is this one, s of lambda y dot z x lambda y dot x. So, we have evaluated up to this one. So, 2 more parameters remain. So, then what we have to continue with this from here. So, now we have x lambda y dot x. Now, we have this yz. So, this is yz. So, now this will be p, this will be q, this will be r. So, then we have to do pq and qr. Pq is lambda y dot x of y. This beta reduces to x, and then qr will be yz. So, then this whole thing becomes xyz. So, then we are done. So, then this is what we are supposed to get. This is b was giving us xyz and xz, this gives xyz. So, that means the term b can be replaced by s applied to one term called ks, another term is. So, we are done. So, now we take up another expression. This is lambda f dot lambda x dot fxx. Okay. This term we have seen possibly when we are doing self application. So, again we assume that this is correct. So, we apply. So, we apply w. So, w, there are 2 parameters f and x. wx parameters will give us fxx. So, that means we have to show that SSSK will also reduce to fxx. When applied to fxx, this will give us fxx. So, we do by, again we work by one term. So, this is first, this is second, this is third. So, this is p, this is q, this is r. So, this will be pr qr. Pr will be s of f, pr will be s of f. Qr will be skf, skf. SKF is this one. So, this we can write as SF, SKF whole thing. So, now we have to do x. That x part was remaining because x fxx. No, fx actually why we applied fx, why we applied fxx, why we applied fx. Now, we have to apply fx actually. This will give us fxx. This is not fxx, this part is x. Okay. So, now we have applied this. So, what we have to now do? We have to apply this x here. This we have to do. So, now then this will be p, this will be q, this will be r. So, I do it here. So, it will be f of x and the other term will be sk of f, sk of f of qr. So, this will be like this. So, this part we have to evaluate sk of fx. So, now here we see what is there. It is sk basically. We can write sk then fx. So, again there are 3 terms. So, it will be kx and fx. It will be kx and fx. Now, what is kx? We have studied kx will be lambda x dot lambda y dot x. This will be kx. So, that beta reduces to lambda y dot x. Now, kx on fx, that is lambda y dot x fx. Y does not occur here. So, this will be x. So, kx fx is x. Kx fx is x. That means this whole thing then we can replace this as fx x. So, then what we have got? Fx x. So, then this also, this part that we have to prove, we have proved that it is indeed the case that it is fx x. So, that means our given terms they are equivalent to the w. Now, let us simplify. Now, the next problem we are going to solve using SKI rules is to simplify given term, that is that algebraic equivalences that we are talking about. So, suppose we are given SKK, can we simplify using some given rules, or we can do it straight away. So, what extent we can do. So, before we do, so SKK will be lambda z, because we are using 2 s, remember we had 3 things, lambda x, lambda z, lambda y, lambda z. So, we are using 2. So, we are going to get lambda z dot k of z and k of. So, we simplify first k of x, k of x. K of x is lambda y dot x, is lambda y dot x. Y does not occur here. So, beta reduction gives us x. So, then this whole thing is boils down to x. So, replace it with z. Now, lambda z dot z is identity function. So, there the skk is then equivalent to the identity function. So, this is one equivalence. So, we have obtained one equivalence on rule. You can say one rule of algebra we can got skk is I for ski simplification. This is one rule we have obtained. Like that we can obtain many such rules. Next example is skmi. skmi. Now again we have s of, you have two terms for s. So, we have lambda z dot kmz and iz. Now, kmz will be, this is lambda a b a m. So, that is lambda b dot m. This will be lambda b dot b. This will be lambda a lambda b. This is lambda a lambda b dot a. So, this will be lambda b dot m. Lambda b dot m z is, b does not occur here. So, this is why we know this rule is m. Iz is identity function, so it will be z. So, then this whole thing will reduce to kmz becomes m and iz becomes z. So, then this becomes lambda z dot mz. Lambda z dot mz. Now, apply eta reduction. S is not free in m, z is not occurring free in m. So, we apply eta reduction, we get this becomes m. So, skmi is m. So, this is again the second rule that we have obtained for. So, this one is a longer term, simpler term. Simplification, we get a simpler skmi. This contains 1, 2, 3, 4. So, we have now simpler term like m. Another example is s, then km, kn. Again we apply there two terms, we get kmz and knz. Now, kmz we know this part evaluates to m. Then knz will also evaluate to n. So, we get lambda z. Now, we applied the SKI rule that said if it is lambda z dot mn, so it will be km. So, now we are treating this whole thing as m. So, this will be k of mn, this will be k of mn. So, then this whole thing then becomes k of mn. So, we have got this our third rule. Now, recall that we said that okay, given a lambda term we want to obtain a term using SKI combinators only. We said that you at some point of the derivation you may need some equivalences. So, these are the some equivalences that we have developed. There are other equivalences. So, these equivalences when applied there you can easily derive a term for a given lambda term. So, I will be requesting all of you whosoever you are working with this exercise. So, please see whether these examples or the equivalences that we obtained can be used for the example that we are trying to solve for B. We are trying to find a SKI term for B. Please make an attempt to solve that problem using this equivalence, or you can also, when you work out a little bit, you will get new equivalences and then you can get the desired result by just performing lambda beta reductions on the terms. So, to summarize, we have discussed the different Boolean operations, all of them can be encoded as pure lambda terms, and next we discussed the SKI combinators and showed how to simplify those terms and how to rewrite a given lambda term in terms of SKI terms. So, we stop here. Thank you for your kind attention.